Welcome to this video on taming the noise in switched mode power supply, or SMPS, outputs. We'll explore a practical design methodology for second-stage output filters based on an analog device's technical article. The real issue isn't the predictable ripple, but the high-frequency switching transients, often at 10 to 100 plus megahertz, caused by fast current changes exciting parasitic inductances. Simply adding more output capacitance is ineffective against this high-frequency noise. A well-designed second-stage filter can significantly attenuate switching ripple and noise, making the supply suitable for sensitive analog circuits. For extremely low noise, a low dropout regulator or LDO may follow the filter. When choosing a filter, the RC filter is best for low output current, providing cost-effectiveness and stability. The LC filter is better for higher current and high performance, offering excellent ripple and noise rejection. Ferrite beads are not recommended as a primary filter. Here are the key parameters and variables we'll use for filter calculations, including peak-to-peak current, target voltage ripple, switching frequency, and allowable transient voltage change. Designing the RC filter involves three main steps. First, set an initial ripple with C1. Next, select resistor R based on power dissipation, noting it should be much larger than the capacitor ESR. Finally, calculate the required output capacitor C2. For currents above 50 milliamps, the LC filter offers superior filtering with low power loss. The challenge is the undamped resonant tank circuit, created by LC1 and C2, which can cause oscillation and instability. The primary task is damping this resonance. An undamped LC filter creates a sharp resonant peak, which degrades phase margin and can cause instability. To maintain stability, the converter's crossover frequency must be significantly scaled back relative to the filter's resonant frequency. We have three damping techniques. The parallel resistor is lowest cost. The series RC network is optimal for performance-critical designs, maximizing attenuation. The output RC network is generally not recommended. The blueprint for an LC filter with parallel resistor damping is an iterative process. Key steps include selecting C1 and LFILT, determining the maximum crossover frequency, calculating capacitance for transients, and finally calculating the damping resistor RFILT. For the LC filter with an RC damping network, Technique 2 offers the best performance. The steps include selecting C1 and LFILT, calculating C2, and then setting and calculating the damping components, C, D, and RD. For component selection, remember that the effective capacitance of ceramic capacitors decreases with applied DC voltage. For inductors, a high self-resonant frequency is more important than inductance for high-frequency filtering. Also, leverage core loss and DC resistance for free damping. To summarize, diagnose the problem as high-frequency transients. Choose the right topology, RC for low current and damped LC for high current. Mastering damping is critical for LC filters, and remember that design is an iterative process requiring simulation and measurement.